Okay, so today, unfortunately, my screen capture technology is not working, so we're going to kind of go with this other system here. So today we're going to talk about real numbers, and real numbers are split up into two main groups, which are rational and irrational. So what we're going to do then is we're going to talk about these two different kinds of systems. Now, we're going to start this with some vocabulary. So let's look at some of our vocabulary. Now, the first thing is when we talk about these rational numbers, they're basically made up into a couple different groups. The first group being natural numbers. Natural numbers are positive whole numbers. So, if you want some examples of them, think of something a positive whole number. If you're thinking, you might be like, hey, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you know what? You're probably right. Here's some examples of it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc., etc. 1,543,000,000. All those are natural numbers because they're positive whole numbers, right? Non-fractions on decimals, and they're positive. Now, another thing that creates rational numbers are integers. Integers are positive and negative whole numbers. If you want some examples of that, then we have pretty much any positive or negative whole number, like -3, -2, -1, even 0 counts as an integer. 1, 2, 3, 4, 5, 6, 7. Basically, you go either direction in whole numbers and you will find integers. After that, we have natural numbers, integers. Well, just thinking about whole numbers in general. There's a cat on the table. Thank you, kitty. I love you. So, after that, we have rationals, or in this case, fractions. A fraction is consisting of an integer numerator and denominator. Essentially, you need a whole number on the top and on the bottom of your fraction for it to be a real rational number. Now, some obvious examples of this would be, hey, like 1/2. Well, 1/2 is pretty obvious. It's a whole number over a whole number, and you guys have seen a half before. Another one would be 3/4. That's another rational number because it's another fraction. Even something weird like -17/42. Well, they could be positive or they could be negative. So just as long as they are a whole number or basically an integer over another integer. Now here's a weirder one that you might see. Is something like 1123/77202 Luna. I tried to make funny on that one. I should have put 773,202. But that didn't work so well. Anyway, but this is still a rational because it's a whole number over a whole number, even though that they're kind of crazy and big. Now, one question I want to ask everyone is 0/1 a rational number? Well, if you put 0/1 in your calculator, what does it give you here? Well, let's try to do that. 0 divided by 1. Well, we still get 0, so technically that is a rational number. But what if we do something like 1 divided by 0? Oh, well, that's undefined. Well, that's a harder case, but technically it's still rational, even though it's undefined because it's 1/0. So it's a rational over a rational, or sorry, a whole over a whole, integer over integer. So then, let's take a look at the next category, which are decimals. But specifically, which decimals? Decimals that end. A decimal that terminates. That's another important word there. Terminate, not like Terminator. Well, that's where it came from. Because if you think about the movie, the Terminator, what did he try to do? He tried to end people in a not so nice way. But so essentially, you're talking about decimals that end. So an example of some of these, well, would be something like, hey, 1.5. Well, 1.5 ends. It's just 1.5. That's it. It doesn't go on forever. It stops. Another example of this would be like 0.3. Yeah, that one stops. It doesn't go on forever. Or maybe something like 1.27.999. This one stops after about 3 nines. It doesn't go on forever. Now, another way to think about these two is that each of these can turn into a fraction. They can be represented as a whole number over a whole number. For instance, 1.5 is essentially 3/2, 3 halves, right? Every one of these can be represented like that. Now, what about -14.44? Well, this is also an integer, right? It's also not an integer, but it's a decimal. It's a rational that ends. So we have -14.44. It stops there. So that brings us to our next category, which is decimals with a pattern. A decimal with a repeating pattern. So they might go on forever, But that's okay as long as the pattern is consistent. For instance, you might see like a case like this where you have a point 3 with a little bar on top. What this bar means is that it means that it goes on and on and on again, again and again and again and again. It's going to be 0.333333333, kind of something like this, where you'd have 0.333333333, and then typically we have like a dot 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 there afterwards because that means it goes on forever. And that's okay because 0.3333333 is actually just 1/3. So if we took our calculator, did 1 divided by 3, hit enter, well, let's hit control enter and it will show us 0.33333333333. But if we kind of select this and move it out, hey, look, it goes even further. It's going to go this way forever. And that's kind of okay because we know that 0.33333 forever is actually representative of the number 1/3, which is a whole number over a whole number. So that makes it rational. Now, another example of that would be, let's take a look at this one. 0.8 with the bar on top. So that means it's going to be 0.8888888. And that's okay. So that's another rational number because it's a decimal with a repeating pattern. Now, let's look at some other weirder patterns. Like this one, if I had something like 0.12 with the bar on top, well, that's going to be like saying 1 2 1 2 1 2 1 2 1 2 1 2, and this thing is a little bit in the way, but there we go. So, but it basically 1 2 1 2 1 2 1 2. It's a repeating pattern. It should usually go dot 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 to kind of signify that it goes on forever, right? Another one I wanted to show was 0.456. Notice how this one would still give us a pattern like 456 456 456 dot 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 forever. Something kind of like that, right? Goes on forever with the same pattern. Now, what about this one here? Is 0.123456789? Does that have a repeating pattern? Now, some of you might go, well, yeah, it kind of does, because 1, 2, 3, 4, 5, 6, 7, 8, 9. But then what would be the next one? It would be 10, then 11. So it might be like 10, then 11, then 12, then 13. That pattern isn't really repeating very well. Now, if it kind of did something like this, where it did 0.123456789, then went back to 1, 2, 3, 4, 5, 6, 7, 8, 9, well then, yeah, that would be a repeating pattern. And then that makes it rational. But in this other case here, well, this unfortunately is not rational. This is something else. This is that other group that we're going to talk about, which is irrational. Now, if you want to think about rational versus irrational, rational, you can kind of think about, hey, those people kind of thinks things through. A rational person would think ahead. It's like, hey, all my friends are jumping off a cliff. I don't know if I'm really down with that. That doesn't sound like what a rational person would do. An irrational person might be like, bro, Dave's going over the cliff. I gotta go too. So now that is totally irrational thinking. So let's look at some things about irrational. Now, one of the first things you know it's a rational number when it has something like a messy decimal. So anything looks crazy, kind of like this one here. It's messy, 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 right? Like there's no pattern or anything to it. They never terminate, meaning that the never end. They go on forever and ever. And usually you can see that when there's like a kind of dot, 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 which signifies that they go on forever. Last thing is that there's no pattern. Those are it doesn't have anything useful like 1 2 3 1 2 3 4 5 6 4 5 6 1 2 1 2, anything that's useful like that. They have no pattern. So like I showed you, some examples of this are this 0.48567392 dot dot dot. Well, we know it goes on forever because it says dot dot dot. We know it has no pattern because I don't know what kind of pattern is happening here. It's also a messy looking decimal, right? So these are one of 3 things you should know. Now, here again, 0.129923 dot dot dot. Oh, it's a messy decimal, goes on forever, no pattern. Now, the world's most famous irrational number is this one that you can't eat all the time, is pi. And everyone should know that pi is 3.14159 dot 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 dot, right? We always kind of shorten it up to about 3.14 because we don't feel like we should write out every single number because it literally is impossible because it goes on forever. So we like to think about it kind of as the world's most famous irrational number. Anything that has a pi in it is irrational. Now, this other one you might not notice is actually called natural log. Natural log is going to be used next year when you guys kind of talk about logarithms. Here, it's just to show you that, hey, it's kind of the same idea where this would actually be e to the power of 1, which would be 2.7182 dot, 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 dot. Goes on forever. Now, ones you might not have seen before are things like the square root of 2. Now, if you're like, hey, isn't the square root of 2 2? No. When we take a square root, remember, you're trying to find two numbers that when multiplied together give us a 2. And if you ever kind of forget this, you can always kind of look in your calculator, like the square root of 2, and whoa, look at that thing. And sometimes your calculator might lie to you a little bit and say, hey, it kind of stopped there. Well, technically, it doesn't really stop. Your calculator is just kind of shorten it because it doesn't want to waste all of its memory trying to get out all of the numbers. But it'll go on and on and on forever. And as you can kind of see as we expand it, 1.414213, blah, 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 blah. It kind of goes on forever. Even though it doesn't physically say dot, 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 we know it's going to kind of go on forever. Now, this will happen with the square root of 3 as well. It's 1.73205 dot, 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 dot. Goes on forever. Now, the next thing I want to ask people is, what about the square root of 4? The square root of 4, is that going to be rational or irrational? If you guys forgot, well, think about it. Are there two numbers that are the same number that multiply to 4? And if you're quick, you might think, oh, yeah, well, doesn't 2 times 2 equal 4? 2 times 2, yeah, that's 4. Are 2 and 2 the same number? Well, yeah, so that means that the square root of 4 is equal to 2. So does that mean the square root of 4 or 2 is irrational? No. This one actually would be rational. Why? Because, well, the square root of 4 is equal to 2, and 2 is a whole number. It's an integer. So another way to think about it is that any of these irrational numbers would be any non-perfect square root. If you forgot what a non-perfect square root is, anything that when square rooted gives us something nice back, that gives us a whole number. For instance, hey, the square root of 1, is the square root of 1 is it an irrational number? No, because the square root of 1 is 1, since 1 times 1 equals 1. Is the square root of 4 irrational? No, because the square root of 4 is 2, since 2 times 2 equals 4. And you can start seeing the pattern. Some of you guys have seen this before when we've talked about these things in the past. So, for instance, 3 to the power of 3 is 9. Square root of 9 is equal to 3. They are opposite sides of the same coin. So essentially, any of these kind of nice perfect numbers, if you take the square root of them and you get something nice, it's rational. If you get something kind of gross, well, then it's irrational. There are more irrational numbers than there are going to be perfect squares. At least there's going to be more irrational numbers or irrational or non-perfect square roots rather than nice, perfect, neat ones, right? So then let's go down to here. So here we have the real system and we have the imaginary system. Now, these are the two main groups of numbers. They're basically the two big houses and two different families. You can kind of think about this as kind of like in science. You can think about it as kind of kingdom, phylum, genus, species, etc., where you kind of have classifications, right? Now, we're not going to talk about imaginary so much today, but that's the other kind of group here that'll be coming up later. So in real numbers is basically everything here. And real has two main groups that we talked about. Here we have rational and we have irrational. We talked about those. Irrationals were the ones that are crazy, messy decimals, go on forever, no pattern, right? So inside rational, well, there are subgroups. The subgroups inside rational are integers, right? Integers were all those negative, positive whole numbers. But inside integers, we can get more specific. We can say just whole numbers. Let me see if I can grab one. There we go. Whole numbers is a subgroup of integers, meaning that it's only things like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then inside whole numbers is even more specific group, which is natural. And natural is the most specific one, which is going to be basically positive integers, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But it basically includes everything except for 0. This one includes everything but negatives. This one includes everything but fractions, decimals. This includes pretty much everything. And real is pretty much everything that's not imaginary. Now, I want to look at some of these things real quick. So sometimes it's good to kind of look at it with your calculator. Let's see, ignore that once. There we go. So I'm trying to look at some of these. Now, the square root of 12. Well, let's take a look at the square root of 12. We'll take the square root of 12 in our calculator here. So take a guess whether or not you think this is going to be rational or irrational. And if you're wondering why I kind of like hold a pause on that word irrational, it's because sometimes when people say rational and irrational very, very quickly, it's hard to tell, hey, are you saying rational or irrational? So that's why I kind of pause on it. All right, so square root of 12. Well, that looks like a decimal. Now, let's see if it actually ends. We can kind of like go on our calculator here, enter. It goes on forever. So now that looks like it's an irrational number. We can say IR for irrational. Oh, that blue line came back. Let's see if we can get rid of it. Ignore once. There we go. All right. What about negative 10 over 2? Well, what group does that belong in? Well, isn't that a fraction? It's a whole number over a whole number. So negative 10 divided by 2 would equal negative 5. So that would actually be a rational number. So it's rational. More specifically, if we think about it, if it turns into negative 5, well, that would be an integer. INT. We'll say integer. All right. Square root of 36. Well, I've been fooled once before. I see a square root. Let's double check it. Or if you're quick, you could think about, are there any two numbers that multiply to 36 that are the same number? And if you're quick, you might know, hey, the square root of 36 is going to be 6. Why? Because 6 times 6 is 36. So 6 is going to be a rational number. In fact, it's a natural number. We'll put nat here for natural. All right, next we have 12 by 26. Well, we don't have to put anything in calculator. That's a decimal. It ends. So that makes it rational. That R looks terrible. There we go. R. Rational. What is it? Well, it actually just is a rational number. So we could just say rational. It's because it's a decimal, it's just in our biggest group of just rationals. All right. Next one is 0.78. Well, this is got that bar on top, so that means it repeats. So it'd be 0.78, 0.78, 78, 78. So that's also another rational number. It's not in any of the more simpler groups. It's a decimal that repeats, so it's rational. 4/9, once again, is, well, that's a fraction, right? It's a fraction, a whole number over a whole number. It's rational. So hopefully these are some good examples that you guys can see. Let's start looking at this one. What about G? It's 442 dot 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 dot. Well, that's a weird case. I think I accidentally made something here. I should have put something like 0.2 dot 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 dot. So that one, well, even though it's a decimal, it goes on forever, and we don't know what the pattern is going to be. So we're going to have to say that's irrational. We don't know what the pattern is going to be. It's a messy decimal that goes on forever. What about this one? This one's a little bit unassuming because it's 303 divided by square root of 2. And you're like, hey, well, it's a whole number over... Oh, I forgot what the square root of 2 is. Well, remember that the square root of 2 is an irrational number. If you guys forgot, you can cheat a little bit here by doing... Let's take the square root of 303 divided by the square root of 2. Well, that one looks unassuming, right? You're like, hey, that kind of ends. Double check it. Because these calculators tend to round things. Oh, there you go. It's irrational. See how it's a decimal that goes on forever without any repeating pattern. Irrational. All right. Negative 9108.2. Well, that one is actually a decimal. It ended, right? It doesn't go dot, 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 and everything. So this is actually rational. It's just a decimal that ends. All right, square root of 140. Well, let's double check this one again. It's always good to check these if you don't know. If you can't think of two numbers that multiply that number, they're the same number, double check it. So let's see, square root of 140. 11.8322. Let's double check. Nope, that one goes on forever too. So that one's not good. All right, so that is irrational. Next one is 88. Well, 88, hey, that's rational. That's just a whole number. Not only that, it's a natural number. NAT, natural, right? Because it's a positive integer. It's a positive whole number. Last one is 0.734292 dot, 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 dot. Oh, well, that's a messy decimal with no pattern. It goes on forever. That is definitely irrational. So I hope that helps everyone out. And I hope that helps you understand the difference between rational and irrational numbers.